Thank you so much, Philippe. Thank you so much, everybody, for giving me this opportunity to talk today. By the way, can everybody like hear me? I know that I usually have like a very like mild voice.
Yes, the transmission is good.
Okay, perfect, awesome. Thank you so much for organizing such a nice workshop and a summer school. I really enjoyed attending it. All the talks were spectacular. So the plan for my talk today is to talk about how to compute Bianchi modular forms. The plan is to just introduce some of the computational techniques that we use for computation, and also show a bunch of really cute, at least that we think cute, examples that we observed from our computations. So first of all, sort of like here's the sort of the big picture, big picture stuff. So there are various different ways, like just like classical modular forms, where how we can like view what a modular form is. I'm not an analytic person, so I'm definitely going to skip over the analytic part. However, I will mostly be concentrating on the algebraic notation as well as the topological notation. Algebraic notation is really good when we want to see how things like the class group gives us some subtleties. And the topological notion is like to view a modular form as a class of homology or a class of cohomology is really nice for computations, which you might already know by now because we've attended Paul Ganas's talks and things like that. So I will be mostly concentrating in these lower two circles. And first, here's a little bit of history. When it comes to computation of modular forms, the classical case was dealt with like Mani, Mazur, and people like that. They talked about M symbols and modular symbols. I should have mentioned those here. M symbols were like the main thing that was used to compute classical modular forms. And our imaginary quadratic fields, there's still some work done. For example, all of these mathematicians, this was in like 1970s, leading up to like 1990s. They worked on computing Bianchi modular forms, which are modular forms of imaginary quadratic fields, when the class number was actually 1. So they actually went beyond even the Euclidean fields. However, this computation was very similar to the computation of the classical case, because when we have class number 1, every single ideal is a principal ideal. So if you want to compute TP for P being any ideal in our ring of integers, if P was already principal, so it was much easier to deal with. So this case was very similar to the classical case. But however, these are the mathematicians who did work on explicit computations for class number 1 cases. And for class number 2, this was Bygott, one of Cremona's students. He worked on class number 2 case. And in like 2005, Lingham, another one of Cremona's students, worked on the odd class number case, which happened to be like the easier case, but easier on quartz, I guess. And much more recently, in 2010, Arnes and Cremona has an unpublished preprint that they were really generous about sharing with us, that actually started extending this work of M symbols and modular symbols, these techniques, to other number fields. And these techniques are basically what we used to compute explicit Hecke eigensystems for our Bianchi modular forms. So just a bit of history, I guess. And here's sort of the setup. So I'm dealing with imaginary quadratic fields, K, with a ring of integers O, and usually I will consider imaginary quadratic fields with a bigger class group. So I will definitely have Hecke operators with TP, where P being a non-principal ideal. And I will concentrate on weight 2 modular forms, and the congruent subgroup that I'm interested in is the upper triangular matrices modulo math frac n, which is an ideal in the ring of integers. So this is very similar to gamma naught n for the classical case, which were upper triangular matrices modulo an integer. This is just an upper triangular matrix modulo an ideal math frac n. And finally, some sort of a definition, I guess. Kargan actually showed that this homology is related to weight to Bianchi modular forms. So at the end of the day, this is basically what we want to compute. And this homology, we have this, like, it's a summer school in cohomology. So we've seen it in terms of cohomology as well. This will give us, and this is just the homological notion of it. And the only sort of weird part is that we are computing with respect to the cusps. But if we relative to the cusp, but if you remove the relative to the cusp part, we are still computing weight to Bianchi modular forms, but they'll be cuspidal modular forms. However, this is basically the homology that we are interested in computing. And this homology, just like in the classical case, we are computing the homology of some sort of like a compact manifold. And the way that we arrive at this manifold is by taking the hyperbolic plane and adding in all the cusps. So these are the cusps to make a partial compactification, and then modding out by the congruent subgroup that we are interested in. And in this case as well, just like the fractional linear transformations in the classical case, there's a nice action of GL2C on the space of points on the hyperbolic 3 space. And this quotient is with respect to that action. So computation-wise, this is basically what we are computing. And the way that we compute is this, we have seen it in Paul Ganas's talks as well. We use the Voronoi tessellation, and these techniques were, the Voronoi tessellation was for the classical case, but however, Ash and Coker had generalized these techniques for the Bianchi cases as well. So we are going to use their generalized Voronoi theory to obtain a tessellation. And this tessellation happens to have, this tessellation is constructed in such a way that the vertices of the tessellation are actually on cusps. So the part that we are taking the relative homology with respect to, which makes it really easy for us to do our computations, because every single edge in our tessellation will become a cycle in homology. And this tessellation gives us a finite list of generators. And also, depending on the geometry of the object that we use for the tessellation, we would get relations as well. So here's like a little example for the Gaussian integers. So this is a famous picture taken from Cremona's thesis. I think this is a picture that is pretty overused, at least I overuse it a lot because it's a very nice picture. This is basically the object that is required to do the tessellation for this Gaussian integers case. So this is we only need for the Gaussian integers, since it's an Euclidean field, we have exactly one cusp optic equivalence, and the number of edges that we need is exactly 1 as well. And there's exactly one polytope that we require to tessellate the entire hyperbolic 3 space. And something to note here is like for higher class groups, this is not necessarily the case for other general number fields and other general imaginary quadratic fields. We might need more than one polytope to tessellate the entire space. And if the field is not Euclidean, we would have more than one cusp optic equivalence. So it'll be much more complicated than the Euclidean case to think about what the tessellation looks like. And another thing to note is like this tessellation obtained by Cremona was using work of Swan, so which is a little bit different. But for the Euclidean cases, the tessellation that you get, like from the Voronoi as well as Voronoi tessellation as well as the Swan tessellation, they'll align. But for other general imaginary quadratic fields, they're not the same. And so I just wanted to emphasize that this picture is obtained from a different algorithm. However, for the Euclidean cases, this is basically the Voronoi polytope as well. Okay, are there any questions or comments so far?
It is okay.
Okay, perfect. I'll move on to the next slide. Awesome. Okay, so we talked a little bit about computation. We are just computing this relative homology that looks kind of weird, but however, we are computing it nevertheless. But what about the class group? So in order to understand how the class group works, we need an algebraic definition of Bianchi modular forms. And this algebraic definition of Bianchi modular forms is very similar to the classical case, where we think about like classical modular forms as functions on enhanced elliptic curves. Here as well, we think about Bianchi modular forms as functions on these general lattices. And this, just like the enhanced elliptic curve, we take a pair of lattices LL prime, and we require one to contain in the other. And the level structure is introduced by requiring the two lattices to contain within one another with an index that is equal to the ideal, which has index mathfrak n, where mathfrak n is again an ideal in the ring of integers. And we use this notation to denote the space of all the modular points, the space of all the lattices that has these properties. And what we can do is we can define what a class of a modular point is by defining the class by identifying the modular the class of the modular point as the Steinitz class. I should have mentioned this is the Steinitz class of lattice. So in particular, we have two lattices deal with. We just pick the notation that we will always go with the Steinitz class of the underlying lattice. So, and this class is compatible with the class that we talk about in the class group. So there's like a nice way of attaching what it means to be a class to a modular point. And this ends up being, this space of modular points ends up being the domain of this general formal modular form that I will define in the next slide. So here is the formal modular point. I should also mention this definition was developed by Arnis and Cremona in their unpublished preprints. And they started developing this theory for formal modular forms. And here's the definition that they have given. So a modular point F, a formal modular form F, it can be viewed as a function from the space of modular points. So this is all of the pairs of lattices. And to C to the R, here R will determine, and here rho is a representation. And the dimension of rho will determine the weight. And what we want a modular form to satisfy is this transformational property that, there is a nice action of GL2C on the space of modular points. And what we want is under that action, we want this nice transformation property to hold. So this should look very similar to the definition of like automorphic forms. And this definition is basically helpful because we can view how the class group comes into play and make things a little bit complicated for us, okay? So the way that we see it is we take the domain. So this is the domain. So the formal modular form, I should mention here that the formal modular form goes from mathfrak n to C to the R. And what we can actually do is we can break up our space of modular points into a disjoint union of spaces of modular points that are in a certain class. So here I have a little typo. This should be just C. I'm not using the CIJ notation. This is just C, where C is just an element in the class group. And what we are doing is basically we are taking all of the lattices, all of the modular points that has an underline that has a class, a particular class in the class group, and we are expressing the domain as a union of those things. Okay. So this allows us to actually view our Bianchi modular form F, which is from our modular points to C to the R, as a tuple of functions where each of these functions will take each of the classes to C to the R. So we are viewing the modular point modular form as a tuple of functions where each coordinate corresponds to a function in a particular class of modular points. Okay, this was that's good. So why does this make it complicated? It makes it complicated a little bit because of how the Hecke operators act on the space. So here's the definition of a formal Hecke operator. So for any ideal mathfrak A, I can define a formal Hecke operator to be this finite sum of things. And here, this is a superlattice notation. We are sort of averaging over superlattices. However, there is a sublattice notation as well, which should look a little bit more familiar than the superlattice notation. And what we can do is if, so this last bullet point is what I want to actually emphasize. So we are defining Hecke operators as functions on lattices. However, by precomposition, we can view it as functions on modular forms as well. And the point to notice is that if I take a Hecke operator, TP, where P is in a particular class, say class C in the class group, and if I take a modular point C prime, a modular point that has a class C prime in the class group, when I do this action, when T acts on, when the Hecke operator acts on this modular points, it doesn't actually preserve the space of the class of the modular point. It actually takes you to the class CC prime. So that's the main issue. So the main issue is that when Hecke operators act on the space of modular points, they don't necessarily preserve the class. So what it means in terms of the Hecke, in terms of the modular forms, is that what a Hecke operator will do is Hecke operator will take that tuple and it will sort of mix things around. So there's like it'll permute where each coordinate will go. And the only things that will actually preserve the class are the principal Hecke operators. So in terms of the computation, they are the only things that we can actually compute, just the principal class. And that basically became like the sort of the obstacle that we had to get through when we had to deal with computations for higher class numbers. Okay, so here's a little blurb about higher class number computations. So the main thing to notice is we have the Voronoi tessellation is already implemented in MACMA by Dainesaki. And there is an analog of modular symbols that we can compute. And here I should add as well as Hecke operators. There's a nice reduction, Hecke operators. There's a nice sort of a reduction theory that we can obtain from the geometry of the tessellation. And it works for this case as well. And so we can compute Hecke operators, we have an analog of modular symbols, and we have a Voronoi tessellation. However, our limitation is that we can only compute Hecke operators TP, where P is principal. So this is like the biggest restriction. However, we are still able to obtain the entire Hecke eigensystem, which includes all the primes where P is non-principal as well, by using properties of Hecke operators. And here are some of the examples that we observe. Before, here's some blurb about the field that we are working in for our explicit computations. So q square root of minus 17 is not a random field because this is the smallest field that has class group 4, class number 4. And we were lucky because it happened to have a cyclic class group as well, which turned out to be nice-ish. And here is a character table for the class group. Just the characters are just the characters of the class group that we consider. And here is some blurb about like the scope of the computation. So we computed relative homology up to norm like 500, and co-operators we computed up to like norm 100. And we computed like bigger Hecke operators whenever we need to prove modularity and things like that. However, for the basic scope of the computation, it's just this. And for this particular field, we did a bunch of computations for a bunch of different levels. And there were various different Hecke eigensystems that we found. And I'm going to share some of those computational results with you guys today. Okay. So here's sort of like one of the first Hecke eigensystems that we noticed. So this is examples of all of the rational Hecke eigensystem. So we know that there is a classical modular form of level 17. And since we already know the modularity for classical modular forms, it's related to this particular elliptic curve. And the isogeny class of this elliptic curve is the LMFDB label is 17A, if anybody wants to look it up. And what we expect is, it's actually what we see is that when I take this elliptic curve and base change it to our number field, it happens to have level P17A. This is one of the primes above 17. 17 is a split prime in this number field, and this is one of the primes about 17. And it just so happens that we observe this Hecke eigensystem at this particular level. So at level 17A, the cohomological dimension is just 1. And we obtain this entire system, Hecke eigensystem for different Hecke eigenvalues. And this entire system aligns with the Hecke eigenvalues of the elliptic curve that was defined above. So I should have mentioned that this is a Hecke operator. Oh, sorry, this is an elliptic curve over Q. And this was a nice example because this is what we expect to see, I guess. And up next is at the same level, something subtle is going on because the homology is only giving us just one Hecke eigensystem. However, in the Bianchi case, there are actually 4 Hecke eigensystems, because what I can do is I can take the characters of the class groups and twist them by the characters of the class group. So these are all the 4 twists that we get. And all of these 4 Hecke eigensystems are valid Hecke eigensystems, and they do correspond to Bianchi modular forms. So this sort of shows the deficiency of the computations in terms of like the homology side, because the homology just gives us one Hecke eigensystem. And something interesting that happens is that one of these twists, especially this particular twist, is the quadratic twist of that first system that we obtain. And that system happens to have rational Hecke eigenvalues as well. So we expect it to also correspond to an elliptic curve, and it does. And this, because we twist the Hecke eigensystem, since the elliptic curve will get twisted, so the level will change. And this happens to line up with this elliptic curve E prime. This should be also over Q at level 272. And this is the class, isogeny class of that elliptic curve in LMFDB, which was pretty cool. And something else. So here's like another rational Hecke eigensystem that we observed. And here's something to notice is like, suppose I take like these two primes. 7 is a split prime in this number field, and P7A and P7B are conjugate ideals. And if it's coming from a base change, we expect these two to have the same eigenvalue, because if it's coming from base change, this will just correspond to A7 in our classical Hecke eigensystem. However, in this particular case, we observed that this is probably not coming from base change, because P7A and P7B, the conjugate primes, have different Hecke eigenvalues. And we observed that we actually proved that it is actually not. This is actually coming from an honest to God elliptic curve that is over the number field, not over Q. So this is an example of a rational Hecke eigensystem that can be matched with an elliptic curve over that particular number field. And this was the case for all of the rational Hecke eigensystems that we observed. All of the rational eigensystems that we observed in our range of computation, we were able to find elliptic curves that matched with it, either elliptic curves over K or elliptic curves over the rationals. Okay. And this was another kind of an interesting, cute example. This was one of the first new forms that we observed. This was at level P2A, and we didn't like really expect to see anything interesting happening in such a lower norm level. However, we did obtain this. And this is where another subtlety sort of comes in. So all of the things on the right-hand side, like all of these primes are either principal primes or primes that has a square that is principal. And it just so happens that all of these principal ones were had rational Hecke eigenvalue. And in terms of cohomology as well, the cohomology of dimension was just 1. So if I was just computing the principal Hecke operators, it looks like it's a rational Hecke eigensystem. However, when we started computing non-principal Hecke operators, we've noticed that the Hecke field is not just the rational. So we don't expect to see an elliptic curve related to this particular level, which is what we would like, which is something that we wouldn't expect to see, because P2A is like a very low level to see an elliptic curve, I guess. All of the, and in terms of the non-principal primes, something that we notice is we need to adjoin to square root of 2, and the Hecke field here was just Q adjoint square root of 2. And another thing that's interesting that happens is, so this is just one Hecke eigensystem. I can twist it by all of the characters to get other Hecke eigensystems. However, there's another thing that I could do. I have a Hecke eigensystem that has a Hecke field that is quadratic. So what if I take a sigma in the Galois group of Q adjoint square root of 2? And what if I twist the Hecke eigensystem? What if I act on the Hecke eigensystem by that? And the question was, we expect it to just have 4 Hecke eigensystems by just coming from the twist. So if this happens to give us a new Hecke eigensystem, we would have like, I can't do arithmetic, I guess. 2 times 4 is 8. We would get 8 Hecke eigensystems. That's too much. We don't expect to see that much. And it just so happens that when I act by the Galois group, this actually aligns with twisting by a character in the Hecke eigensystem. So acting by, this is the conjugation, at least the non-trivial one. So acting by the Galois group of the Hecke field actually aligned with twisting this Hecke eigensystem by chi2, which is the quadratic character, which we thought was pretty cool, because if we were just doing the computations for the classical, if we were just computing the principal Hecke operators, we would have thought that this was a rational Hecke eigensystem, but honestly, it's not. Okay, and I think I'm like almost out of time if I'm not wrong. So I think I'm going to like stop here and see if y'all have any questions or comments for me. Thank you so much for your attention.
Thank you. So, any questions in the classroom or on the Zoom chat? No. I'm just wondering, so when you, your implementation was done in Magma?
Yes.
As the one of Dan? Okay. And,
yes.
But so did you did you more experiment than just q square root minus 17?
So I think our code will actually work for other fields, but I didn't do any other explicit computations for other fields.
But
the code is definitely like I could run it for other at least class number 4 fields I can definitely run. But other even class number fields, I might have to work a little bit to figure out that there are some subtleties that I need to figure out to like generalize. But yeah, for the time being, it looks like the code that I have written depends very much on the structure of the class group.
Not that much on the size of the discriminant?
Yeah, so kind of, I guess. Sorry, can you repeat that question? I'm so sorry.
I mean, let's say, okay, I rephrase it. What is the influence of the size of the discriminant on the computation? So in particular on the running time of the computation?
So I am not very sure about that. Yeah. Yeah, I haven't done enough experiments on like different number fields. I'm not sure about that. I'm so sorry. That would be an interesting thing to look at. I'm sure there are people who might have looked at it.
Okay. No further questions? Okay. Thank you again, Kalani.
Oh, of course. Thank you so much for having me. This was a really fun experience.